So you're going to need your notes package for Unit 2. If you haven't printed it, it's online. Just go into the classroom folder there, and it'll be in there. Okay, Unit 2 notes package. So today we're going to talk about the most basic part of Unit 2. Okay, Unit 2 looks at a lot of the same movements that we looked at in Unit 1, but now we're going to look at them from the point of view of the forces that cause them to happen. Okay, we know the movements happen, we know speed changes, position changes, all that kind of stuff, but now we want to look at why. Why does the speed of an object change? Why does its position change? What are the forces that are acting on the object that cause that to happen? So our focus will be, what are forces? How do they work? How do they affect the movement of objects? And then at the end of the unit, we'll go into work and energy, which means, okay, where does the energy come from to exert said forces? All right, so that's what we're going to be looking at now. All right, so we're going to start off talking about Newton's first law, which, while part, and a very important part of rocket science, is definitely not rocket science. Okay, Newton's first law says this: this desk will stay right here, provided nobody moves it. Okay, well, duh, of course it's going to stay right there if nobody moves it. Okay, but this is like, if you're, early on, you get into science early on, you get to think up all the simple stuff. Okay, Newton's first law is summed up usually in one word, okay, and that word is inertia. Okay, inertia is the tendency of an object to continue doing whatever it was already doing in the absence of any unbalanced forces. Right? For the desk right now, all the forces acting on it add up to 0. Okay, their vector sum, if I put them all together, would be 0. Because right now, as long as Kelvin doesn't kick it, there are only 2 forces acting on the desk. Okay, if I was to draw what we call a free body diagram, which is something we use all the time, if I was to draw that, it would show the 2 forces acting on the desk. Okay, now you're probably thinking 2 forces, Codere? Like, I don't think so. Like, what forces are acting on that desk right now? Gravity's acting on that desk. And what else? Well, air pressure kind of acts on it equally from all directions because it's surrounded by air. I could put that on there, but it'd be hard to draw it. If there was only gravity acting on the desk, what would it be doing right now? It would be falling. Okay, what's keeping it from falling? The floor. Okay, that force is what we call the normal force or the reactive force. Okay, it's basically part of Newton's third law, which is every action has an equal and opposite reaction. We're not going to talk about that for a couple weeks yet. Okay, but because gravity is pulling the desk into the floor has to push back with an equal but oppositely directed force. That's why the desk stays where it is. Okay, this is the force you can feel right now on your butt from your desk. Gravity is pulling you down into the seat, and the seat is pushing back. Okay, everyone follow me there? You can feel it in your feet when you're standing. I feel it right now. Okay, I can feel the floor pushing against my feet. I don't feel gravity pulling me into the floor. I feel the floor pushing back. I feel a force directed upwards against my feet. Okay, if I push harder against the floor, what will I do? I'll have more force upwards, which means I'll jump. Okay, you always probably thought right up until now that in order to jump, you pushed up. You don't. You push down. Think about it. Okay, when you're getting ready to jump, you bend your knees and you press against the floor, and the floor pushes up against you with an equal but opposite force. Now that force is greater than gravity, and you accelerate upwards until you leave the floor, and then gravity, stupid pesky gravity, pulls you back. Okay, the stronger you are, the higher you can jump, because the more force you can exert against the floor. Okay, I said I wasn't going to talk about Newton's third law, and then I get caught up in it. Anyway, okay, back to Newton's first law. Okay, so Newton's first law says that an object will continue doing whatever it was already doing if all the forces are balanced, okay, if they all add up to 0. So a stationary object stays stationary because all the forces add up to 0. What if I have let's say, a rock floating through space. Will it just continue to float through space? Yes. Okay. Until it's acted upon by an unbalanced force, it'll continue to travel in a straight line forever, because there are no forces to speed it up, slow it down, or change its direction. Okay. Now, most of the time, an object will change direction because of what force? Gravity. Yeah, gravity will eventually pull something towards something else. Okay. But if I had, like, an infinitely long distance where no gravity would act, an object would travel in a perfectly straight line. Okay, and it would do so at a constant velocity. Okay? So if you've ever watched the paint drying curling championships that were going on, okay, here last week, if that ice is perfectly frictionless, curling becomes even more boring, because what will the rock never do? All right, exactly. It'll never stop. Okay, curling is actually a skill testing sport, because you have to figure out, okay, how hard do I have to push this rock? How do I have to spin it in order to allow the very small amount of friction that's present in the ice to slow this thing down where I want it to stop? Okay, that's apparently exciting. Some people really like it. I think it's pretty boring, but whatever. Okay, because there isn't any air. Yes. It literally is empty space. Okay, so there's no air to exert any resistance of any kind, right? Makes sense? Now, if you were to go through like a nebular cloud or something like that, where there's a bunch of hydrogen gas, then there would be some small amount of resistance, not a lot, because the gases are pretty spread out. Okay. And even in the upper atmosphere, where it's very thin, there's enough air there to generate huge amounts of friction against re-entering spacecraft. All right, so this is inertia. Now, why does your car have all the safety devices it has? So you don't die. Okay, that was the obvious answer. I probably should have specified that. What does it keep you from doing in a crash besides dying? Flying out of the car. Okay, you fly out of a car if you're not belted in because of inertia. If I'm not wearing a seatbelt, the car stops. There are unbalanced forces that stop the car, that change its velocity. If I am not attached to the car by a seatbelt, my inertia is to keep moving forward at whatever speed I was moving at when my car stopped. Okay? Now, there will be unbalanced forces that will act undesirably on your body if you are not attached to the car by your seatbelt. Those forces would be the windshield, okay, the other cars, okay, the road, and things like that that are going to hurt a lot. Okay, you need to wear your seatbelt. If you don't wear your seatbelt, that's crazy and illegal, but mostly crazy. Okay, you need to wear your seatbelt because it is, like, always, I want to say always, but I mean, there's that one guy that didn't wear his seatbelt and lived, and he only lived because he wasn't wearing his seatbelt. That's like that 1 in 10 billion chance. Okay, it is always safer to stay in the car in a crash. All right, so we consider, like, when we start thinking about safety devices, seatbelts are usually the first thing that comes to mind. Okay, the next thing that comes to mind is what? Airbags. Yeah, okay, airbags. Seatbelts keep you in the car. They also slow you down more slowly than just stopping. Okay, seatbelts actually stretch a little bit. Okay, if you're going more than 50 kilometers an hour when you get into a crash, you'll have to replace your seatbelts if your car's not a write-off, because they do stretch. Okay, the airbag does the same thing. Okay, the airbag is there to prevent head injuries. Okay, which is why now, like, when a car gets into a crash, it blows up in all directions. Like, it's not just the steering wheel now. There's a curtain airbag that turns into a cannoli. Okay, when you get into an accident, it just explodes from everywhere. But that's to prevent your head from striking any of the hard parts of the car. Okay, in the early days before airbags, okay, you would see a lot of people who had the same kind of scar. Okay? You'd have a scar right here, right across their forehead, okay, on their scalp, and that's the steering wheel scar. Okay, when you got in a car accident, and we didn't have, like, we only had the lap belts. Okay, then not all cars had the shoulder belts. Okay, you'd go forward and you would strike the very rigid steering wheel, and it would scalp you. Okay, it would literally cut you here and peel back your scalp, and then they'd have to sew back on. Okay, so a lot of people would have that same scar right there. Okay, so car manufacturers went, well, that's not good. That's not very safe. Not only do you have this big scar, but you usually have a bad concussion and things like that. So they designed steering wheels to collapse, which was smart. The only problem was if you got really angry and had bad road rage, you could collapse your steering wheel. I had a buddy, and he hit it really hard with his fist, and it just folded. Okay, he had kind of like this cool-shaped steering wheel after that. It had a dip in the middle. Okay, yeah, it's kind of like just with the two handles on the side. But yeah, you could collapse it, but it was better if you hit that with your head and it had more padding on it. Because I mean, if you look at like a car built in the '60s, like this, like it's metal wrapped in like hard plastic or wood. It's like really hard. This stuff would be padded in plastic and would fold down if you hit it, which prevented a lot of head injuries and things like that. But it still wasn't as good as, an airbag. An airbag is not a pillow. Okay? If you've ever had one blow up in your face, it doesn't feel soft. Okay, it explodes and violently smacks you. Okay. In fact, if you're driving and it goes off, you'll get bruises on your arms where it hits you and throws your hands off the steering wheel. Okay, and then you'll go into it. But when you hit it, you decelerate a lot more slowly than you would if you hit the steering wheel or if you didn't have an airbag at all. Okay, so airbags are good and they protect your head. Okay, they lower the inertia of your head slowly as opposed to rapidly. Okay, and we don't want that rapid change, okay, to happen.
So why does it matter if it's like a smaller child being hit by an airbag?
And that has to do with the next safety feature, mass. Okay, when an airbag detonates, it detonates with a lot of force. And I say detonates, it is an explosion. Okay, there's a little electrical thing that detonates this stuff called sodium azide, which releases nitrogen gas very rapidly into the airbag. Okay, so it does explode. It's 120 decibels. Okay, so when the flames score at the Saddle Dome, that's about 110. Okay, and the scale is exponential. So 120 is like 10 times louder than that. Okay, it's really, really loud when they go off. So your ears will be ringing for sure after an airbag goes off. But yeah, it explodes outwards. If you're a small child and it hits the car seat, it can actually crack the car seat. It can break, their bones are not as hard yet. They haven't ossified completely, so it's very dangerous for them. Plus the rapid acceleration, the seams in their skull haven't grown together yet. All that kind of stuff can really cause bad head injuries for small children. Plus they don't have much mass. Okay, and so they feel the force, the acceleration caused by those forces a lot more than you or I do as a grown person, right? That's why you have to be like 75 pounds to sit in the front seat. Okay, because airbag can hurt you otherwise. I suppose it could. It's not likely. I mean, that's essentially what it's designed to prevent, right? It inflates very quickly, but it's not a balloon. Okay, it also deflates very, very fast. It explodes outwards, you hit it, and it starts to deflate almost immediately because it's full of holes. Okay, and so it deflates really fast. They can't have that thing stay like that because you could be pinned by it or suffocate by it if you're knocked unconscious, right? So it has to deflate quickly. All right, so we've talked about some of these other safety features, but we haven't covered the most important safety feature in your car. Okay, obviously, brakes and airbags and seat belts and stuff like that are very important, but the most important safety feature is what? Mass. Ever see a smart car win a crash with a truck? They can't. It doesn't even matter how fast they're going. They can't win that because they don't have mass. Mass is who determines who wins and who loses in a crash. And make no mistake, there's a winner and a loser in every crash. Okay, that's why I drive a truck. I want to win. Okay, I'm very competitive, and I want to win if I'm in a crash. And I've been in a couple, and they weren't my fault. Okay, and I won them. Okay, I won them all because I drive something big and heavy. I don't care how much gas it uses because I have small kids, and if I get in a crash, I want to win because that means they're going to be safe. Okay, we once had an accident where we were going speed limit even, okay, 60 kilometers an hour, and a lady, I don't know how she didn't see my big SUV coming, but she turned right in front of us, left turned right in front of us. I had no chance. Basically didn't even get to hit the brakes, okay, before I just smashed right into her. She was driving a small little, like the Ford Focus, like small little sedan, right? I mean, my Ford Expedition at that time, cut into that car like a hot knife through butter, okay? Like it just cut into it because I had so much more mass, okay? And mass determines your acceleration. My acceleration was so small that even at 60 kilometers an hour, striking almost head on, my airbags didn't go off. Hers did. And the crash that started in the middle of the intersection ended my direction in the other side of the intersection. Okay, so my velocity changed, but I continued to move forwards. Her velocity changed and she changed direction. Was her acceleration a lot worse than mine? Yeah, it's acceleration that kills you, not the force. Okay, when a smart car and a semi-truck hit each other, the forces are equal. The force experienced by the semi-truck and the smart car are the same. What's different is the accelerations of each. And the acceleration of the smaller mass is always way greater than the larger mass. Okay, it's acceleration that gets you. Okay, that kind of makes sense to everybody? All right. So before we go any further on that, I'm going to show you a little video on why you don't want to drive a smart car.
So if you have like two objects that are the same mass, would they just bounce off? Like
Yes.
same speed?
Yep. Exactly. So if I had two like identical, vehicles, let's just say like two, Ford trucks hit each other. Okay. Then yes, the accelerations will be the same. Okay. The forces will be the same. The accelerations will be the same because the masses are the same. Right. Now, if I have one of those trucks that's loaded up with cargo and the other one's empty, then now this one with more mass experiences less acceleration. Okay. All right. Okay, so the inertia of an object is related to its mass. That's why we were saying mass is the most important safety feature there is. Okay, changes in inertia require a force. So if we're going to slow something down, then I have to exert a force on it. Newton's first law only deals with situations where there are no unbalanced forces. All right, so if I'm sliding along a sheet of perfectly frictionless ice, all the forces are balanced. Okay, gravity pulls me down, the normal force pushes me up. There's no friction, so I just keep sliding. Okay, nothing stops me until I hit something or there is suddenly friction or something like that. Everyone kind of follow? All right, what does that mean for you if you're an astronaut and you get separated from your ship? You're screwed. Okay, that's why they almost never do EVAs where they're not tethered. Okay, because if anything happens or they run out of maneuvering fuel, because usually the suits have small jets on them that they call RCS or reaction control systems. Okay, they allow them, so they push and a little jet of gas comes out and it pushes them the other way. They can maneuver a bit with those because obviously just doing this in space doesn't do anything. So they have these little RCS thrusters. But if you run out of fuel and the fuel is just gas, okay, like any type of gas, oxygen or hydrogen or whatever, okay, then you have no ability to maneuver anymore, right? If you're not tethered and you're not touching the space station, you're screwed. You'll float away, okay, because there's nothing then at that point you can do. All right, so you have to have, they almost always have people tethered, okay, when they're doing EVAs. Chris Hadfield, when he was the commander of the International Space Station, okay, he did an EVA where he was almost lost. Okay, he had, they had put oil to lubricate the visor in his helmet, and it's I don't know what kind of oil it was, but it's they put it on there, and when he put the helmet on, some of it came off, and because they're in zero gravity, the little droplet of oil just floated over and got in his eye, and it immediately caused his eye to water and close, and he couldn't see, and he was outside on that doing his EVA, and when his eye started to water, because again, he was in zero gravity, he was shaking his head, the tear rolled across his nose and into the other eye, taking the oil with it and irritating the other. He had both eyes he couldn't see, right? And so here he is, he's got, he's still got maneuvering fuel, but he can't see where to go, okay? So he was, I mean, in an astronaut way, still kind of calm, cool, and collected, but obviously getting a little frightened in that I'm blind and I'm outside the space station in my suit. How do I get back because I can't see? Okay, not tethered. Okay, that kind of stuff because he was doing a job where he couldn't be tethered for some reason. So what they ended up telling him was, that thing, Chris, we told you never to do. About like venting your suit to space and exposing yourself to the vacuum of space. Yeah, you have to do that. Okay, and that's what he actually ended up doing. He actually ended up cracking the visor seal, okay, open manually, so that all of the tears and oil would be blown out of the suit by the pressure in the suit into space. Okay, and so it took all that stuff, and then he was able to close up the suit again, and after a few seconds, he was able to see enough to get back in. Right? But it was pretty scary for him. Yeah. All right, so if I get separated from my ship, then I float away. All right, this is why, if you ever become an astronaut, never go out on an EVA unless you are carrying a big, heavy tool. Always take a big, heavy tool with you. Okay, remember I told you this when one of you becomes an astronaut. Take a big, heavy tool. Why? Throw it in the opposite direction. Okay, and do it like a chest pass, kind of like this. Okay, push it away from you. If you throw it like this, you'll rotate. Okay, and you'll look very not graceful. Okay, so if you take a big heavy tool and you push on it, okay, what does the tool do? It pushes back on you. That's Newton's third law. So you would move in the opposite direction that you throw the tool, at least a little bit. It might be enough, okay, to get you back. Not going to be very fast, but it might be enough to change your velocity, just enough. All right. Now, I once had a kid who also said, well, then why would you ever let it go? Why wouldn't you just keep doing this? Because every time you stop it, what happens? Right, it reverses what you just did when you tried to push it. So yeah, you can sit there and do this in space. You'll look like you're dancing. Maybe you'll look cool. I don't know. Okay, but you got to let it go. Okay, you got to sacrifice the tool. All right. So looking at this then. Okay, what are forces? Okay, very simply, a force is a push or a pull. All right. Anytime there's a push or a pull on an object, a force is being exerted on it. Okay. The vast majority of the forces we'll deal with in this course are what we call contact forces. That means the object has to be in contact with the thing exerting the force. The one exception to that will be gravity. Okay? I don't have to be in contact with the Earth, physical contact with the Earth, in order to experience its gravity, because gravity is a field force. You do a lot more field forces in physics 30 when you deal with electricity and magnetism and things like that. Okay, all the other forces will be contact forces. Right? Friction is a contact force. You have to be in contact with something in order for it to rub on you and cause friction. Okay, if you're using that bulldozer, you have to be in contact with the wall to push on it. Okay, if you attach a cable to something like this, okay, it has to be in contact in order to exert a force. All right. So some things will push, some things will pull, some things are capable of doing both. A rope is not. Okay, this is what my old physics teacher in high school used to call Mr. Hill's first law of physics. You can't push on a rope. Think about it. Tie a rope to something and then go like this. Right? It doesn't work very well. You can't push on a rope. A rope will only exert a pulling force unless you roll it up into a coil, set it against the thing, and then push. Okay, but then you're not really pushing on the rope. Okay, you're pushing through the rope. Okay, so gravity also, okay, would be a pulling force. All right, so gravity is a pulling force that acts on an object. So in this case, a projectile. All right, so a force is a push or a pull. Okay, mass also important. Okay, mass is the amount of matter possessed by an object. Okay, it is not how heavy you are. How heavy you are is your weight. That's different. Weight is a force, not the same thing as your mass. But that's another one of those North American, we're saying it wrong all the time kind of things. Because when somebody asks you how much you weigh, you immediately tell them your mass. You tell them in pounds or kilograms what your mass is. Okay, here's a great way to never have someone ask you that question again. Actually tell them what you weigh. Okay, when someone asks me that, I tell them I weigh about 730 newtons. They chuckle awkwardly, look other places, and then go talk to someone else because they think I'm weird. When in actual fact, I don't have to give them an answer they'll understand, but I also haven't lied. I have told them what I weigh, even though that's not a nice question to ask somebody. Okay? So, if you ever want to get out of that, that's how you do it. Okay? Take your mass in kilograms, multiply it by 9.81, that's your weight. Okay? In newtons, that's what you can tell people, and they'll leave you alone. They won't ask you that anymore. Okay? All right, we're going to talk more about that later, but not today. Okay? See you guys later. Take